So these are the 5 different kind of DP states that you should be familiar with. And in the last session we talked about this LRDP state, right? That where you have for the subrange L2R, what is suboptimal answer or something that you keep in the DP, right? Apart from that, we have styles like knapsack, where you have I comma weight or I comma sub cut straight into the problem. We have DP of I comma anything, even nothing is also valid. Okay, so this type of states is seen in LCS, LIS, and all those things. Sorry, not LCS, LIS, and sub array ending at index I, so on, right? Now, for LCS or string related problems where you have 2 different strings and you need to compute something along with that, 2 or more than that is also possible, right? Even if there is a third string, you keep a k, right? So for these kind of problems, you can use uh, state something similar to like this, where you have I and j, where you have string word prefix I and prefix j. Okay. Now we also discussed about game-based DP, where you have for the game state, is it a winning state or losing state, and based on that, we talked about how we decide on whether it's winning or losing. Right? Now these are the fundamental states that you need to understand. Okay. Of course, just knowing the names of states and types won't help you. You need to apply them into the problem and understand that, okay, first of all, like given a problem, which of the class will it go into, right? And then inside that class, you need to fill this dash, right? There is a dash written over here. Also, we don't know what are we keeping as the answer in the DP, right? There can be multiple things that can be kept in the answer. So designing it comes after that. But first of all, you need to think about, okay, which style of DP is most suitable for this kind of problem, right? And this thing is first step that you need to learn from practicing problems. After that, next step would be to decide on what do you keep along with things to help you to solve the problem, right? Now, what do you keep mostly comes from recursion, that what are the things that you need in recursion to create solutions. Okay. Now, one way that you can think about these things is, let's say you want to, let's say, write a brute force code for some problem. Okay. Now, well, when you are writing brute force things, generally like you have the full solution that you have created till now in the recursion stack, and like you can keep a vector as well, right? You can keep a vector if you want to, and whatever you have taken till now, and at any particular step you can see to the vector and find out what can you do with the elements over there and all, and then based on that you can decide on things, right? So these vectors can be there, but the optimization that we do in case of DP, while coming from like recursion to DP, is that we try to rule out things that we don't need in recursion, right? So one obvious optimization that I think all of you now know is memorization, right? That save the recurrent state answer so that you don't need to recompute it. The next thing is removing things in the brute force that you don't need, right? Like this vector might not be relevant. You don't need to even keep track of that. Just keeping track of the sum of weights in knapsack is sufficient rather than keeping all the elements taken till now, right? Like in case of LIS, keeping the track of, let's say, what was the last element is sufficient because you will extend on that, right? So this is kind of optimization that we are doing on recursion to build our DP states. Once you understand this, you are basically doing the same recursion, but with this smaller set of information that you keep, that is required to compute the answer after that, right? So that's the only difference in DP and recursion. Okay. Now, of course, like I think we discussed this on the chat as well. So if you're feeling like your recursive thinking is not working, like not up to the mark right now, you can take up some problems like, okay, you have something called AVL and something called heaps. Okay. Now these are 2 structures which are like, you can read about them on any like algorithm book, and you can understand what these things are doing, right? Now once you understand what these things are doing, go about implementing them without looking into any other code. Now in AVL you need to do a lot of rotations of nodes. Okay, like you need to rotate, something called left rotation and right rotation is there. So how do you maintain that balance in trees? How do you maintain the balance in the trees along with all these things in place is something that you can like think out on your own and write a recursive code for that. Now in recursion, the main thing is like create a function, delegate a task to it, that what that function will do, and use this like as a sub problem, as a subroutine in the same function efficiently, right? That's what you need to do. Same goes for heaps and other things. So this is what you need to understand in recursion. Now, what is your function? You just need to be clear that what are the things that my function will take, right? What are the things that I will take, and what is my function, and what will it ensure? So let's say if in an AVL tree I'm saying that it will get balanced. So something like, let's say in a space it's there, so you break it into smaller space and you say that okay, I will apply recursion on this and it will make this property to hold on this part, and using these smaller properties that are getting holded, I will like create a method to maintain the bigger property for this, right? That's what my recursion is doing. That my recursive function will take something and will give me this property correctly. Now how will it give me that correctly? That is what you have to design using some smaller subproblems and other things, right? So if you're thinking that you should work a bit on your recursion part, take these two structures. They are fairly straightforward. Like if you just go through one video or like just read what are the operations that you need to do, you will get a hang of it, like what is being done. Okay, it's just you need to work with implementing it correctly. So once you get that, I think you will get to understand recursion. Okay, now also it's some deeping problems where you are thinking about okay, what should my recursion, will it work or not? It's a good idea to sometimes write there are two things that you should be doing. Something called write on a notebook, that whether it will work or not. Try to take three, like n equal to 2 or n equal to 3 items, and even if it's like a brute force, you check that okay, whether my brute force kind of code is working well with the DP as well or not. Okay. And the second thing is print code, like print intermediate states. Okay. Now this is something that you should understand because this will help you in debugging your DP codes as well. That printing intermediate states. So let's say you wrote a DP code and then you found out that okay, my DP is giving me a wrong answer. Okay, like it's not giving me the correct answer. Of course, you need to know the input in which it's failing. That's the first thing. But let's say you know the input and your answer is like wrong. So how do you go about correcting your code? So print like most of the states, like something like let's say knapsack. So in knapsack you generally have this criteria, right? That okay, uh, after I number of moves, I have all my weights, like which all weights is what is the maximum profit that I can make at each weight, right? This kind of sub profit values are given is there. So is it at knapsack basically when you're solving it in DP at every level I, it ensures that answer using all the items from 0 to I is what is given at that point, is be calculated at that particular state, right? So this is some property that the DP is maintaining. Now, once you know this, just check incrementally that whether it's working or not, right? This is something you can check when you're getting a wrong answer on a code, right? Similarly, for these DP, like let's say LIS. So is my ith ending getting correct or not? Okay, is my subarray is my smaller subarray getting a correct value or not? Is some prefix of this string is giving me a correct value? Is the smaller distance of the game giving me a correct value, right? So these things is something that you can check, and this of course you can check using printing the intermediate values, that how is it being calculated, or you can just let your recursion create everything and then print the memo table that you are creating, or you can just directly use the function to like print whatever states is relevant, right? So these things you can just have a look at. Okay. Also sometimes like if you're not getting a hang of how this recursion is working, you can write a like just write out a simple code, right? How is the stacks working? That's also something you can look into, but I think these two should be sufficient enough in most of the cases. So with these things discussed, let's quickly go about solving sub problems. Okay. So now this is some like a vocabulary that we will have from now on. Okay. That we know that these are the 5 kind of states that is there. Now we will try to, like whenever we see a problem, try to first of all recognize okay, which class of problem, class of DP state will it go into. Okay. So around 70% of the DP problems that you would be seeing in most cases would go into one of these classes. Okay. It's like almost true. And like if you go into some medium to hard states, we will cover those things after this. Like there are 3 more states. If I append those 3 more states, it is more than 90% of the problem. Like it's around 90% or 91, 92% of the problems. Okay. Still there are 9% that are hard and they take non-trivial states into account. But of course, like first of all, you should target to solve the majority of them, right? So from now on, these are the 5 states that you should try to think about, that okay, is this state going to work in this problem? Okay, once you know the class, think about what else do you need to keep in that particular problem so that it works. Okay, uh, after you decided that, how will you, like, of course, along with taking things, you will also have to think that how will I create the value and what is the value that I will store. Okay, that what is the longest integer subsequence ending at index I, so or something like that. Okay, maximum profit that I can create. Okay, so what's the property that you are maintaining, that your function is maintaining. That's it. Okay, is everything clear up to this? Can we start with the problems then? Can I have a quick plus one? Okay, and if you're not feeling like comfortable yet with DP, don't feel a problem. Like it does not come in like 1 or 2 sessions directly. Like it's not even just that 10 solving 10 questions is going to give you confidence on DP. It is not supposed to be like that. It will take incrementally a lot of time, but it will eventually be like it's a masterable skill. It's not something that you cannot solve. Okay, now let's talk about first problem. So let's talk about this particular problem that uh, you are at a number one. Okay, you are standing at a position one and you want to go to position n. Okay, if you're standing at a position x, you can either go to position x plus 1. Okay, you can go to 2 into x, you can go to the position 2x. Okay, or you can go to the position 3x. Okay, make sense? So these are the 3 states that you can go into from this particular state. Now you need to find out that what is the shortest number of steps that you need to go from uh, the first position to the nth position. Okay, so this is the 3 kind of operation that is allowed to you, and what is the minimum number of steps you need. So we will go slow. This is the first problem, so it's a bit easier, might be easy for some of you, but still we will talk about how are you thinking about forming the states and what to keep in the DP. Okay, now let's say how, so any ideas what do we keep as the DP state and what is like, so whenever I ask that what should we keep, the ideal answers format would be something like the states with some reasonable variable name that suggests what that state is and what is it storing. Okay, like minimum jumps, minimum steps, or something like to reach some index I or something like that. Okay, any ideas what should be, so like if you want to type something, this should be your format. Okay, more or less. Okay, that's correct. That's one of the styles that we will discuss. So dp of I, distance of what to it. So by distance, I am assuming that you mean that minimum number of steps that you need from 1 to n, I to n. Right? Okay, so this is one particular state. Another possibility would be something like, let's say dp of I says what is the minimum number of moves that you need from 1 to I. Like what is the minimum number of moves you need to come from 1 to I, some particular state I, right? Like you can jump twice and come to I, right? This is another possible state. So this is the kind of flexibility that you have, that okay, you have the power to decide that what should be your, like even though like I is same, you have the liberty to decide that okay, do you want to keep I to n or 1 to I, right? Make sense? This is something that you have a liberty on. Okay, in fact both will work. Okay, if you go back to some of the problems that we have discussed in previous sessions, in most of them I must have taken that okay, I have done up to first I elements and then I have some property maintained. Okay, you can even think about that in this sense that I have done the last I objects and I have some property maintained, right? So a lot of states in DP are like the order of the things can be reverted. Okay, now out of these two, there is not a big difference with that it will give you, like in terms of writing code. It's just whichever you prefer, right? So how many of you are like confident that you can code both of them, right? Okay, if I keep like 1 to I or I to n, both of the ways you will be able to find out the answer, because if I keep I to n, the answer would be dp of 1. Okay, if I keep 1 to I, answer would be dp of n. It's just like the final answer is going to be this. Okay. So how many of you are confident that you will be able to code both? Okay, no one. That's at least one of them. Okay, fine. So in fact, it's more or less same for both of them. Like both will be more or less same. There is no difference. Let's talk about dp of I means 1 to I. Like what is the minimum state from 1 to I? Okay. So when we are saying that we can add that sub index, like this is a general notion that whenever you see a problem in dp, if you're saying that add that I, how can I add that I? I must have either come from I by 2, okay, I by 3, or I minus 1, right? These are the only three states that I can come from to this particular state, right? From this, I must have made a move of 1, I would have made a into 2, I must have made a move of into 3, right? These are the three moves by which you can come immediately, right? And others would be some possible, like the last move that you must have done would be from one of these three states for sure, right? So just take like the minimum of 3 and do a plus 1, right? So I will be dp of I will be minimum of dp of I minus 1. uh, Now there are some conditions over here that these should exist. Of course, only if I by 2 exists, then only there is a possible transition from that state, right? Like if I is an odd number, then how is I by 2 going to exist? So of course this only exists if this is odd, but provided that if it exists, like if I is not even, then we don't, if I is even, then we don't consider this into recursion, right? It's not floor. Okay. Only if I mod 2 equal to 0. Okay. This is I mod 3 equal to 0. Only if this is there, then this comes in the bin. Okay. And of course, in DP, you need to think about base cases. So DP of 1 would be equal to 0. That coming to 1 is 0 cost, right? You're starting at 1, right? Now, the other way around would be similar. Let's say you are at an index I, and what is the minimum number of steps that you need to go from I to N? So you can either go to I plus 1, you can go to 2I, or 3I, right? These are the three states, and from there you will continue your journey to N, right? Some journey. So with these in place, you can think about, yeah, this is going to be plus 1. Yeah, sorry, there should be a plus 1 over here. Like all of these with plus 1, right? Okay. So in this as well, like whatever is the minimum length from I plus 1, you can append once jump from I to I plus 1, and you can get a possible like transition from I, right? So this is again going to be dp of I is equal to minimum of dp of I plus 1. Either you go to I plus 1 after this, or you go to dp of 2I, or you go to dp of 3I, okay, at plus 1. Okay. Now in this case, the coding would be a bit easier because you can handle both of these with a simple check that if you go to some dp of I, if it's greater than n, then return infinity, right? This is just a simple check, and with that you can handle this. Make sense? So keep in mind that in most questions, when you're thinking about dp, you can take it in both orders, but just think about, just like fix on one and then implement one. Okay, it's not like don't get yourself puzzled in between that. Okay, whether I'm keeping from 1 to n, 1 to I, or and I to n, whatever I'm keeping, just be clear on one, and based on that think about it. Okay, just how am I extending it? That's it. Okay, is this question clear to everyone? This is, I think, like this is fairly simple to implement, so we will not be going into this. So now let's start with the next problem. So let's say you are given a parenthesis sequence, okay, that you are given a parenthesis sequence, but some of the positions are not given to you, like it's marked uh, question mark, okay. Something like this. Makes sense? So now at each of these positions, you can put any one of them. So find out the number of assignment for like the total string. Like you can replace question mark with either opening bracket or closing bracket. Okay. So find out the number of assignment that you can do such that this particular parenthesis sequence is a balanced parenthesis sequence. Now I hope all of you know what balanced parenthesis mean by now. That's nothing but like there should be like always a proper like sequence that okay you don't have like something like this, okay, where like at some prefix number of closing bracket is more, or you don't have a unclosed ones. These are two not valid. Okay? That's everything. So find out number of assignments of this particular, like let's say this is a string given to you. Find out number of different ways in which you can replace the question mark such that it's a balanced parenthesis. Okay. So what do we keep in this? So keep in mind this is what we've been looking at. So there are five choices. So by now I think most of you have remembered what they are. Okay, so the question is like you are given a sequence, let's say something like this. Let's say I give you something like this: question mark, question mark, question mark, question mark. So how many like ways are there to replace this question mark with a parenthesis symbol so that this is a balanced parenthesis? So one way would be to replace it like this. One way would be to replace it like this. Okay, and there are only two ways in fact, with just four question marks, right? So you will be given a string in which there are some of them are already fixed, like some of them are already given, and some of them are question mark. So find the number of ways in which you can replace the question marks so that you get a valid string. So for this string, the answer would be two. There are only two ways. Right? So for any general string, find out the number of values. So forget about complexity and everything. What do we keep to solve it? That's first of all important. Like you should first of all think about any one solution and then optimize it. That's a different case. But first, how do we even solve the question? Like one possible assignment in this would be, so I have closed, closed, closed. I can open one over here and then close one over here. So this will get closed. So this is one possible assignment with this particular string. So how many assignments are there? Okay. So just this is what you need to think about. So what type of state would be helpful in this particular? Think about this. Take 1 minute, or 1 or 2 minutes. Think about it. Okay, any ideas? So how would we solve this in case of like just a brute force code? Like how would you even go about solving this in a brute force fashion first of all? Am I audible? Check. So can one of you quickly confirm that is the screen visible and am I audible? So how do we even like go about solving this? Like, what would be the choice of brute force code for? Like, how do you even do it in a brute force fashion? First of all, any ideas on how do we do it as a brute force code? That's like I've even accepted brute force for like what? How do we even solve this for brute? Any ideas? I mean, brute force should be something that you should be able to think in this particular problem. That how do I do a brute force? Okay, that's a valid proposition that for each of these question mark generate, like let's say there are 5 question mark. Okay, let's say there are 4 question mark. So what you will do is you will generate everything, like every possible like assignment that is there, like all 2 to the power 4, and just put it in this place and check the last one, right. That's one possible way to implement this brute force. uh, so we will try to write the brute force in this fashion that okay, in most of the brute force when you write, one way would be to like start from the first, keep going forward. Whenever you see a question mark, either replace it with open bracket or close bracket, then move, keep going ahead, right. There are 2 to the power 4, and when you reach the end, you have built the whole solution, right, that you have decided for everything. So just check that particular string whether it's correct or not. Okay, so basically what I'm saying is something recursion of like which position I am at, position. Okay, like I have something like question mark, okay, something like this. Let's say let's replace this over here. Okay, I have question mark over here. So position and uh, my current like up by build string, okay, by string. Okay, so let's say this is the input string, but I am building a string from the start. Okay, and I will keep on start. I will go from the first position. I will keep going ahead. And at each position, if it's already a character, I will just use that character. If it's a question mark, I will try both. I will place something like this. I will place something like this. And then based on that, I will decide later, right? So if I keep building this, when I reach, like I will call recursion of 0 comma empty string. Okay. If I call this, I will reach at some position, I will reach, okay, recursion of, let's say, this is of length 1, 2, 3, 6, right? So I will reach 6, and I must have decided all of the question marks by then. So I will reach with substring like, let's say, this, sorry, this. Okay, something like, I placed both of these question marks as closing bracket. I reach this particular state. Okay, and when I reach this 6, I know that I have decided everything. So just check whether this is a valid string or valid uh, uh, Palace parenthesis sequence or not, right? That we can do in linear time. Okay. Is this recursion clear to everyone that what we are trying to do? Can I have a plus one quickly if this is clear? So if this is clear, then we are more or less on the track. So we will try to use this same state for DP. But the thing is, there is this string that we want to store, right? Now the number of different strings that it can generate is pretty large. So we don't want to keep string in the parameter, and we will try to optimize on that parameter too. Like what do we keep instead of the string itself to build the answer? So at a particular position, like what is the thing that is, so we are building with empty sticks so that like every position when we reach at that position, we will either place like opening bracket or closing bracket at the end. Like we start with this, and then when we come to first position, like zero is this position. So I will place question mark and then go to the next level that I have to place rest of the things. Remember at quiz problem, we just place quiz level by level. That's how we are doing. So instead of keeping this string, what should I keep so that it helps me to build the string? Like it's going to, so eventually what is the thing that we need to do at the end? Check whether it's a balanced parenthesis, right? Yeah, yeah. So what possible will be the number of opening minus number of closing? Okay. So now we will understand first of all one thing, that how do we check whether a sequence is balanced or not efficiently. Okay. So if you, like, this is a very important conversion that will help you in a lot of problems. Just like, I think most of you know that how to check a balanced parenthesis sequence using something like stacks or something like that. A very simple way to implement it without using any stack or anything would be just convert every opening bracket to +1, convert every closing bracket to -1. Okay. Add any sequence is valid if you start from 0, if you end at 0, and you never go below 0. So it's a valid parenthesis sequence. Okay. So what I'm saying is, like, take a string, something like this. Okay. So start with 0, then you encounter +1. So you get to a level 1. Okay. Then you get to level 2, then you'll get to level 1, and then you get to level 0. So basically, I'm just adding whatever the value corresponding to the character is. Okay. So what I say is that this sequence that you get, if you start from 0, you end at 0. Okay. And if you never go below 0, that's a balanced parenthesis. Is this clear to everyone? Why is this working? Right. So this is like a quick correspondence between like balanced parenthesis sequence and uh, numbers. So you don't need stack and everything to check. Okay. So now how do we use this information into our place? So at every position, we just need two things, right? That, okay, at every position, it should not go less than 0, and at end, it should be equal to 0, right? So what if, like, when we were building the parenthesis sequence, we started with 0, right? We are 1, we are 2, we are 1, we are 0, right? So what if we keep this number? Because this is going to decide, like, if we know the last position's number, based on this particular character, we can decide on this particular position's number, right? Like, what is the number of unclosed open brackets till now? So this number is nothing but number of unclosed open bracket, right? Number of open brackets that has not yet been closed, right? uh, Something like number of open minus number of closed at variable statistic. Okay. So what if we keep track of this particular number? Because this is what is going to help us decide throughout the sequence whether it's valid or not, right? If at any point of time we go less than 0, then we know that, okay, it's not a valid parenthesis sequence. Okay. And finally, if we reach to 0, we know that it's a valid parenthesis sequence, right? Without going below 0. Make sense? And so we will keep like a count. Okay. So we will call, let's say, recurrence of 0 comma, initially the count is 0, right? From this, let's say, like, there is subsequence like question mark, okay, that is a closing and closing, let's say. Okay, right? So when we come to the first character, it's opening, so we have to place an opening, so we will always go to this particular state. Okay. From this, we will always go to this particular state because it's opening. So at position 1, we don't have a choice. Okay. Now at this position, we have two choices, that we can either go to recurrence of 3 comma 1, that by placing a closing bracket, or we can go to recurrence of 3 comma let's say 3 by placing a opening bracket, right? From this again, let's say we place a closing bracket for the next one, so we go to recurrence of 4 comma 0. From this, or we can place an opening bracket and we can go to recurrence of 4 comma 2, right? This is, so basically, if we are placing a closing bracket, we are doing a +1 or we are doing a -1. At every question mark, we will get a choice, or for rest of things we don't have a choice, right? 3. Okay. after this, like once we have placed two question marks, let's say after this it's fixed that you take a closing bracket. So we will reach recurrence of 5 comma minus 1, right? But this is something that's not valid. As soon as I get to minus 1, it will say that okay, there is no valid sequence, return 0. Okay. If I reach to this, then I will reach recurrence of 5 comma 1, okay, because it's a closing bracket over here, and then it's again a forced closing bracket, so it's recurrence of 6 comma 0, right? So I traverse the whole length and I got to 0. So this is a valid sequence, so I will return 1. And this counting 1 will return, like total count will be there. Like this is how we were writing the brute force. So this is just the same thing in an efficient manner, right? Is this all making sense? So we basically write a DP recurrence, something like this, that okay, we will write DP of position I and number of open brackets, okay, number of unclosed open brackets. Okay, this is the DP state that we're keeping, and this will store the number of valid sequence with this after this configuration. So you have placed the first I and you have reached this configuration. How many different ways are there to place the rest of the things so that it's a valid sequence, right? That is the number of valid sequences after this. Okay. This is what we are keeping in the recurrence. Okay, and just memorizing it will give us like let's say the length of the string was n. So number of open bracket sequence, number of open brackets can be at most like n by 2 or less than equal to n. So there would be order n square number of states, right? And for every state, we have at max 2 transitions. Like at a position where it's already fixed, you have no choice. So you just do whatever the bracket is saying. So you go to that state, like something like this. That you know that it's a closing bracket, so you have to go to 1, right? It's a closing bracket, so you have to go to 5 comma minus 1, and then from there you check if it's like a base case that you check that should I return like a 0 or should I process further, because as soon as I go to minus 1, it's done. It's like you are not able to solve, like it's not a valid balancing sequence anymore, right? So that's all. Just this is how we are doing the whole DP things that we have been discussing till now. So till now we were building up the concept of states, what the states are and what are the standard states. This is how you basically go into solving the problem. That first of all, think about in terms of recursion, that how do I do it in the brute force way? Now what is the most unoptimal thing that I'm doing in the brute force? Why am I like not able to save the brute force and optimize it? Because I was saving a whole string, right? That number of strings can be very large. But think about this, that let's say there is 4 question marks, okay, and let's say at this particular position you were at x. So even if I place something like this, you will reach x. Even if I place something like this, you reach x. So after this I plus 4, let's say this was I and this was I plus 4. So I plus 4 comma x is repeated multiple number of times. So this is where I'm doing the optimization, and that's why DP is coming into play, and it's helping us to reduce the time complexity. Is this all making sense? Can I have a plus one if this is all making sense? Okay, fine. So today we'll not be going into implementing all of these things. Like implementation is straightforward once you know the DP and recurrence. Okay, it's just putting down that recursion. Like it's very similar to writing the brute force just with a memorization. Okay, so that we have already discussed till now. That for these type of states, how do you code it, right? That we have discussed in the previous session. Now once we know the states, we will directly say that okay, this is the state. You just need to implement it. But how do you build the intuition to come to that state? That's what we will be taking up this in this session, right? Okay. Uh, so this is all about this particular problem. Okay, so in brackets, so and after this, after you have solved this particular problem, now you know that in bracket kind of problems, that when you have to count the number of sequences of brackets or something like this is kind of a state that you should use. That okay, you need to keep the number of open brackets till now. Okay, something like that. So once you know this, then for any new problem that you see related to brackets, you understand okay, this is something that I can keep in the state, right? That's how it builds up. Okay, makes sense. So now let's move to the next problem then. So let's talk about this particular called. Let's say you are given a string. Let's say A B, okay, something like this. A string is given to you. You need to find the number of distinct subsequences of the string. Number of distinct subsequences of the string. So if I quickly list down the number of distinct subsequences, subsequence means that okay, this is a subsequence. This three is a subsequence. Okay. So one length subsequence would be A and B only. If I write two lengths, the AB, TB, AA, right? AB, all four are possible. For three lengths, there is some problem like ABB is possible, AAB is possible, BAB is possible, and that's all right. Three lengths is there is just three subsequences. Um, AAB, AB, B. Sorry, ABA is also possible, right? Yeah. But for four length, it's just what ABA. So in total, there are 10 subsequences. Sorry, 11 subsequences that are possible. Okay. So find the number of distinct subsequences that are possible of this particular string. So in general, the total number of subsequences would be 2 to the power n, right? Like 2 to the power n minus 1. Number of distinct subsequences, number of subsequences that are possible. Okay. So we are talking about number of distinct ones. So that would be 2 to the power n. So it's less than 2 to the power n minus 1 because some of them are repeated, right? And some of them are not possible. That's it. Not necessarily. This is not a new technique if you think about it. It's just like a way to write the brute force, right? So it's not something like you are breaking from smaller to bigger to smaller or something like that. We basically, so you are going from bigger to smaller in this case as well. It's just in a disguised form. It's basically we are having. Let me just quickly handle this. Yeah. So till now, what? So basically, this also like when we are saying recursion of 0, comma what is the opening or closing, we are basically saying that okay, I have this much of unprocessed computation to be done. This much of unprocessed computation needs to be done, right? Based on what we are deciding, like once we place the first character as opening bracket, I'm saying that okay, this is the computation this is the smaller problem that I have to solve. Okay, so it's not like we are going from smaller to bigger or something like that. It's reducing the number of possibilities after that only. So the number of possibilities after that is smaller compared to the initial ones, right? So it's from bigger to smaller only. It's just the way in which you are implementing the brute force. That's it, right? So in a lot of such brute force, like when you are solving DP problems, at least try to keep this position, or if you think about this in terms of states that we discussed, this I. So build it iterative, like build it from like indexes wise, like with the first few elements, what is the answer? With the first let's say I indexes, what the answer? That's a very standard type of style of writing the brute force as well as DP. Okay, so this DP comes from the brute force style itself. So it's not like something new. This is just like optimizing that, like keeping that string to opening brackets. That's all. Okay, but we are going from bigger problem to smaller problem only. Okay, it's never like it's never the other way around. Like more possibilities to less possibility. That's it. Okay, that's all. That's what we are. Basically, the number of ways to get a balance prices on this is same as number of balance prices with this with a one opening bracket. That's what we are saying. Okay. Okay. Coming back to the problem that we have to find the distinct subsequences. Think about this for a problem for a minute. So if you have any idea, you can write on the chat. Yep, that would be a good way to generate. Okay, so if you're thinking like start from the recursive way, like how do you even like write a recursion for this? Uh, like start from the last character. I'm personally starting from the first character. It's equivalent if you start from the last character as well. Okay, so when I implement things, I generally prefer to start from the first, like start from zero and go towards the last, something like that. Okay, it's just a personal preference. You can start from the last character as well. Okay, we will like this will it will make much more sense with the first character, last character, starting from the first itself. Okay, so let's say you have this only. Okay, so basically what I'm saying is we will try to like keep a set of like what are the subsequences that are correctly created. Okay, and we will append a new character at the end of all of them. Okay, so let's say a brute force way to generate the solution. Okay, let's say a brute force way in which how we can generate. So when we come to like initially, let's say there is an empty like I not say empty set. It would be an empty string. Okay, there is just an empty string in the set. Okay, now you come to this character. So the idea is take whatever there is in the set and add that same string appended with a. Okay, so this would get a new string that is there, right? So basically the idea is all those strings that we can generate till now, just append this new character that we are finding at that particular index and insert that back into the set. Okay, so currently you can either create an empty string or a single string, right? Next we will go to b. Now you take out everything that you can create. Okay, and for this particular string you can append b to this, so you will get b. And with this you can put ab. So this is the set that we currently have, right? Make sense? Now we will come to this particular character. Now we can append a. So now note that what is happening over here. If we append a at the end of this, we are getting this particular string, but it's already there in the set, right? So the thing is, don't append it again. Like don't like this is a set. So one thing does not appear twice. So we don't append a at the end of this because it's already present, right? So there is a match like at this index. There is a problem with this particular string. Like if we append a at the end of this, it is going. It's already present in the stack. It's already present in the set, right? That's what I'm saying. Okay. With b, if I append a, it's not already present, so I will add that. Okay, ba is added. Okay, with this ab, so aa, right? After this, if we add aa, so it will become aa, right? So it's not there. With ab, if I append a, so it will become aba. That's not present already, right? So if you think about it, for this particular prefix, these are the distinct subsequences that are there, right? So basically, we are for every index incrementally building the set of distinct subsequence that we have, right? Is this making sense? What we are trying to do in a brute force fashion? Is this making sense to everyone? Can I have a plus for if this is making sense? Okay. Don't think about like first when you're starting with the problem, be no in no hurry to get the like answer right away. Think about how do you write the recursion, start optimizing it. Okay, now with this particular string we will start appending b. So we will see that okay, after this particular, so I will mark this one with green. So with this, if we append b, we will get b. So this is like colliding. Okay, if after b we append b, we are getting something new, so that's okay. This will be bb. Okay, this with this we will get bb. Now, so I'm writing these new strings in a separate place. Okay, just to make a claim after this. So BB is going to get added. Okay. With after BA we can append B, so we will get BAB. Okay. With after this A, if I append B, so it's going to repeat. So that's not going to add, right? So I'm going to, anyways, I will redraw it later on. Let's say uh, this we are done, this we are done, this we are done. B A B B is something that we are getting new. Okay. AAB is something that we are getting new. Okay. AB AB is something that we're getting new, right? These are the things that we're getting new. Okay. Now, if I'm just redrawing this with with a different diagram, just like a different uh, format. Okay. So we have the strings A, B, A, B. Okay. So I'm writing this in terms of like what are the different strings that we generate after each step. Okay. So there was a FT thing. Then we generated A in this step. Okay. So then we generated B in this step after by appending this with this, and we are generating AB at this step, right? At this particular step, we are generating, since A was already there, appending with this is not making sense. Okay. Uh, Appending after A makes sense. Okay. After B makes sense. Okay. And after AB, A makes sense. Okay. This all three is this diagram clear to everyone, that after each character we are basically like writing which are the news elements that are getting added. Okay. So first of all, a quick observation that like at a particular character, like potentially it will try to add the number of distinct substrings that are there till now, right? Like the number of distinct substrings there are till now, just double them. That is what it should have been, provided that there was no repetition. Okay. Is this all making sense? That like till now, whatever is the number of distinct substrings, that is the number of new distinct substrings that we will try to, that it will try, this character will try to generate just by appending this character at the end of every one of them. Is this clear to everyone? Can I have a plus one? Like we will build up this very slowly so that this becomes clear and you will remember this forever. This is a very, like this is a very important technique. Like distinct kind of problems are asked in a lot of problems. Like whenever you need to maintain distinct in a DP state, this is what you should be thinking of. Okay? So all these things is going to get appended with things. So whatever the number of distinct substrings till now is, we will add plus one to this. Sorry, we will add that many strings again to the count. Okay, something like that. Okay. Now, what are the strings that are not going to get generated? How do we count that? So we are appending A at the end, right? Think about the time where the A appeared last time over here. So what I claim is whatever was the number of strings that we generated till that particular position before that, appending like whatever strings there were till over here, appending using this A at this A is going to give us the same strings, right? Like let's say there was some number of distinct substrings over here. We would have tried to append A at the end of all of them, right? Now, if for these strings we are again appending A, that is same as appending this A, right? These two A have like no difference in real life. Like it's just two characters. There is no difference between these two A. So all these strings are the strings that are going to get repeated. Okay. If you think about it, this empty string is what that is generating this A, add a A from this again, right? Let's try to look into this particular case that you have this B. Okay. So till this position, you have 1, 2, 3, 4, 5, 6, 7. Okay. So we will try to generate 7, but some of them are repeating. Which are those repeating strings? If you think about what is the last time B occurred, this position. So if you see, empty plus B is what is repeating because it's already generated, right? A plus B over this is repeating because it's already generated. Make sense? Is this clear to everyone? That first of all, it will try to generate, like it will try to double the number of strings in the set that is there currently, but things that are repeating would be of count equal to the number of strings that was generated till the point last time the same character appended, right? And you can see that this is exactly the case in this particular string. You can write more examples. So sometimes if it's not clear that whether this will hold true or not, write few examples. If you cannot write it on a notebook, write a code. I think by now, like, writing brute force should become easy. Like, just like keep a set, take out all things, append the character, and put it inside a new set, and print the set after every step. I think this every one of you can write, right? A is not repeating. So A is not, like, I'm not talking about A. A plus this character, right? A plus B. This is repeating, right? AB is already generated over here, and this B is generating AB again with this string, right? Okay, that's what I'm talking about. Make sense? So all of the strings that are generated till now will be, so this B will try to double every one of them except the strings that were generated before the last time this character occurred, because all those have been extended by this same character once. So why extend it again with the same character, right? It's going to give us the same thing. And we are using the last occurrence because that's the time, like, that's where the most of the, like, distinct substrings were going to get the first, like, the last B at its end, right? So it will count all these strings that are going to repeat. Makes sense? Like, there was no B before it in between, so that there cannot have been overcounting of things. Okay, so this is just to remove overcounting. But I hope this is something that is making sense. That we just wrote a brute force only first. That there was this set that we were, like, writing a brute force, right? We had a set, take, like, whatever there is in the set till now, create a second set two, take out everything and append B, keep those in the set two as well, and that is your new set. Okay, so we were building that set incrementally. So this is a brute force with 2 to the power n size. Okay, from that we observed that for a particular character, the strings are trying to, like, basically it's like appending at the end. So it's like 2 into the number of subsequences till now minus what are the strings after which you will append B will repeat in the set. That is nothing but all those strings that were generated before this last occurrence of B. Okay, so this is one like, every time we optimize some brute force to some DP, like, that is going to help us in, like, after memorizing it is going to be like some states are overcounted and we get the benefit of DP. It's always going to be like there is some brute force, there is some small observation or small or large observation. I think this might be a non-trivial observation that if you subtract the last one's distinct subsequence, it's going to work. This is a bit non-trivial, of course, but again, once these are things that you need to know once, and then you can think about these things again in a new problem, right? There is always a first time for these things. So this particular idea that for the last character whatever is there is repeating, this is kind of the observation that is allowing us to, like, optimize this brute force to a well-formed DP state, right? So now if you think about it, we no longer need to generate these, like, sets in true sense. Like, we don't need to keep these strings in a set. We can just keep a count, right? So we can just keep, like there is this a b. So we can just keep a count that, okay, from up to this point there are two strings, right? Like, initially there was just one string, empty string. Okay, so later on, empty string is trivial to remove from state. Like, we just remove that one count at the end. Okay, so there was one empty string. After appending a there was two. After appending b there was four. After appending a there would have been answer would have been equal to, like, double of this, like 8 minus the number of strings that appeared before this a. So find out the last occurrence of a. You can keep track of 26 last characters, right? For this particular index, what when this character appeared last. So just subtract this number, 8 minus 1, that is 7, right? So this is going to be the number of distinct substrings. Okay. For B, this is going to try to double this. So this is going to be 14 minus the last time B occurred, this particular number. So it's going to be, sorry, this particular number. So minus 2, 12, right? So there are 12 final number of distinct substrings in the set, and one of them is the empty substring. Okay. So the answer would be 11. Is this clear to everyone? Can I have a +1 if this is clear? Now tell me, like, what would be the time complexity of this particular implement? Like, if you implement it in some fashion, like, there is no big DP in this. Like, we just need counts of things. That's it. So at every index I till that character, what is the size of this distinct substring? That's what we are storing in DP DP is like a big overkill in this. Once we get this observation, it's just keeping a prefix count kind of thing. So what is the complexity of this? So yeah, order of length of string, correct. That's if in some question, if I'm not taking something, you can say order n means the length of string. That's it. Okay, so order n, because like for every character, like you can keep a track of the last time this particular character occurred. That's very simple to build, right? Where was this last this time that where was the last position this character appeared? That you can, I think everybody of you can build. Okay? And with that, we just need to subtract two numbers, like double this 2 into last minus last, like 2 into I minus 1. So you can write it something like this: dp of I will be equal to 2 times dp of I minus 1, okay, minus dp of last occurrence minus 1. Okay, this is the last position, like this is the position of last occurrence minus 1. This is the dp that it's using. Okay, is this clear to everyone? So if this is clear, then I think like this is one of a very like important question, as well as some a problem that a lot of people is not won't be able to get their mind cleared off. Okay, if you're clear with this, I think you can safely say that you are understanding well above average for sure. Okay, in DP, like even someone who has gone through DP completely. Okay, make sense? Now we will take up another problem. So today we'll not be moving into implementation a lot. That's why I had to like take the first few sessions without going into these details of DP, because unless you get to know some amount of what we are doing, like it was all about like just getting some hang of it, so that what we are keeping in states, how we are implementing the recursion, that's all that you had to take out from those sessions. Like you can of course repeat it now to get a better understanding, but this is what is more or less like discussing states and how do you design the DP, right? This is what you should take away in that, right? This is what is I would say crux of DP. Like this is how the thinking that we are going right now is the way in which you should think about DP. But unless we would have done like discuss the codes a bit and what are the standard states and other things, we could have gone into this discussion directly, right? That's why I think some of you might have been feeling that DP is tough till now. I can assure you that after going through these things, like it would be straightforward. Okay, okay, not straightforward, but still. Okay, so let's now start with some format of problem, that is sequence countings. So let's say you are given like find out the number of n length sequences such that each character is either let's say 0, 1 or 2. Okay, and at each position, so you need to find out the number of sequences of 0, 1 or 2, right? Each position can be either 0 or 1 or 2, right? Let's say 3 lengths. Let's say you want to find 3 length sequences such that no two neighboring position have 1. Like this is not valid. So two consecutive positions should not have 1. Just the character 1 is bad. Like having two positions back to back with 1 is invalid. Rest everything is valid. Okay. Find out the number of such sequences of length n. Is this clear to everyone? So basically you need to find the number of ways to assign every position either 0, 1 or 2 such that no two neighboring position has 1. That's all. That's the question. So think about this particular problem. How do we like keep something in state and use it? Any ideas that what do we keep in states? Like, how do you go about doing a brute force similar to what we have been doing till now? Huh. So in fact, something similar to this came in the last algorithmic contest as well, I think. Or if it has not come, it will appear. But the main idea is that okay, we can like if you go about doing this in a recursive style, like just doing it in terms of brute force, the simple way would be to just like dp of, sorry, I'm not writing dp right now, let's say recursion. Okay, so this would be recursion of, like, you are at position I, and what is the string that you have created till now, like I'm or let's say what is the vector that you have created till now. Okay, that initially you are starting with an empty vector and you have to decide for all these n positions. Okay, so let's say you are starting with, I'm just writing in this fashion, that you are starting with recursion 0 at position 0 of n positions. Okay, and you are starting with nothing in the stack. Okay, let's say you place 0 over here. Okay, so you come to the state, like if you put 0, you will go to the state recurrence of 1 with an 0 in the first in the vector, right? This is what we have decided till now. After this, let's say if you place 1, you will go to the state recursion of 2 comma 0 comma 1 has been placed, and what is the answer, like what are the like, so this basically state will give you, will return the number of ways in which you can place the rest of the numbers, right? That's this recurrence is returned. Okay, so this particular will return that the total number of ways in which you can fill all positions, right? So a basic way would be to write, like, just go through this brute force. At the end you will reach some n comma some like assignment. Okay, check that this assignment contains no consecutive ones, and you are done. Like if it contains no consecutive ones, then return 1 or else return 0, right? This is the base case. Okay, so this is how you are designing the recursion for this. But of course recursion is not something that we are looking forward to in this session. Like it's not the most optimal step at which we will stop. So now with this particular thing, we will try to look into some ideas. So a better way to write this recursion would be to, like, after this particular step, if I it's no point in putting another one, right? Like, I know that the last element is 1. So in this sequence, last element is 1. So why to put another one? Because it will create this vector, right? Now, whatever you do after this is always going to be invalid. So it is always going to return 0 at the end. And everything in this recursion stack will return 0. So why to even put a 1, right? Like, so whenever the last element is 1, just ban 1. Okay. Rest everything is valid. Okay. Now, once this is established, there is one more observation that you can look into, is that, like, when you are at some sequence like a b c d has been pushed and you are at the last position, it can be either 0 1 or 2, right? So the next character's choice that you can put into, like, you can put 0 1 2 at the end of this, you can put 0 or 2 in this set. Okay, you can put 0 1 2 at this set. Okay, so this is only depending on the last character that you have in the sequence, right? At this recursion parameter, what is the last character, that will only decide that what you can put in the next character, right? So that you get a valid sequence. So if we why to keep track of everything that we have seen till now, drop off that all of these things, just keep the last character that you have taken, and that will decide what you can take in the next step, right? That's it. That's the whole optimization that you need to do in this particular problem. So keep, like, going from this brute force recursion, that position comma keeping the vector, we are moving into the style that, okay, I will keep recursion of 0 comma last character, like any position comma last character. What is the last character that I took? Okay, so I can initially call it with, like, let's say I was at 0. Like, initially, let's say I hypothetically create a 0. So I have 0 seen and you have 0. Okay, so because after 0 all of the 3 characters is valid, so that's why I'm just calling it with 0. Okay, so from this we will try to put 0 1 2. If the last character is 1, then you cannot put 1, so you will only call recursion of 2s and all. Okay, so from this position you can either go to recursion of, like, what you have placed one more character, and you go to, like, ending at 0, so on, right? Ending at 0, ending at 1, ending at 2. when you are at, like, let's say if you are at some state like recursion of 1 comma 1, you cannot put another 1 at the end of it, so you can only go to the states like recursion of 2 comma 0 or recursion of 2 comma 2, right? That's all. So if in this case, you in this way you write the same recursion, and at the end, if you can in some valid way reach some recursion of n comma something in the last character, then it's a valid state, so you return 1. And everything, if you memorize, it's done, right? Like, it's recursion of some pause comma last. This is the correct recursion, and for each of the position, like, you just need to keep, like, this can take order n values, and this can take 3 values. So in total there are order n into 3 states, and for each of the state you have like at most 3 transitions, so it's order n only, right? Make sense? So this is how we are doing it in some of the problems. Like, even if you, some of the problems that we have discussed in the previous sessions, we might not have gone into this particular discussion, but this is what we are doing. That, okay, we are like, we are first of all trying to do it in the brute force fashion, and then we are dropping off the things that we have taken till now, because the last character is what is mattering, right? So if you think about knapsack, it's not the choices that we have made, but the weight of the total choice that we have made is what matters, right? That will decide on whether what we can take in the next states, right? So that's the whole idea of like going from brute force or recursion to BP. Okay. So is this problem clear to everyone, that how we solve this in order n? Can I have a quick +1 in the chat if this is clear? Okay. So if this is clear, then we are done with this one. Let's start with this style. Let's talk about this particular problem. That, let's say the setting is saying we have n positions, okay, that we have to fill with, let's say, just zeros or ones, okay, and the only constraint that you have is there is another input given k, okay, so no k consecutive positions should be ones. Okay, find out the number of different sequences that exist of size n such that no k consecutive positions are 1, or no k consecutive position. Let's make it a more general. No k consecutive position is same. Okay, so it's like you cannot have more than, like, greater than equal to k consecutive zeros or greater than equal to k consecutive ones in the sequence, right? Apart from that, everything is allowed. So find out the total number of sequences, and kn and k is given as the input. Is the question clear to all? Think about this one. Okay, so now I think a lot of you are maximum number of consecutive ones, maximum number of consecutive zeros. So Amisha, the problem with your state would be like, how do you decide on, like if you know the maximum number of zeros and maximum number of ones, the problem is it's not extendable to I plus 1. The reason is, let's say there is some sequence of let's say something like this. like there is a bunch of maximum ones over here and maximum zeros over here. Let's say these are the maximum ones, maximum zeros, okay? And then you are placing somewhere over here, and there was one over here. So like let's say you placed one over at this position. So how do you decide on that? Like, is it going to create a new maximum of ones or not? Okay. So maximum number of ones can be at this place or this place, right? Like it's not yet decided. So it's like most of the things that we are taking up today, like abhi, like last 2-3 questions that we have been taking up, these are mostly of the form this, like if I go back to this, that it's more or less I ending at I, more similar to this particular knapsack style, that we just don't have a condition. It's the condition is different over here, like it's not some weight or some summation, it's some different condition. Okay? What is the last thing that we have seen? Okay, so keeping the max won't work, like just the count of max won't work. We need to find out what is the so rest of the state should be working. Once we can place start with k and keep increasing.
The same as what Amisha said, but instead of maximum number of consecutive ones, the number of ones we can place would be k, the beginning, and number of maximum zeros we can place would be k. And as we keep adding ones, that will keep decreasing, and the other one will remain k. So
yeah, that's more or less correct. That's a valid state. That will this regression will work. Okay, let me. So I will quickly summarize what. Oh, sorry. So the state that like Ashish and Tejas are what we were looking into mostly, but what this particular state that just now when you suggested would be like DP of like uh, I comma allowed once, allowed zero. So in that case, whatever is the last character that you have placed, so let's say you have been placing 3 ones till now, and let's say k is equal to 5. So you are basically at the state dp of whatever position you are at I comma. You can place 2 more. Okay, let's say 1 more. So it should be less than k. Like there should not be no consecutive k possible. So that means less than k. So you are allowed to place 1 more, and zeros you can place 5. Sorry, 4. Okay, you can place 4 zeros. So now from this particular state we can say that okay, if I place 1, okay, that means I'm going to extend this to 4. So I can go to this particular state that I comma 0 comma 4. Okay, now I can also place 0. So in that case I am placing 0 over here. So now my new, like this particular 3 got reset. So I will now have a limit of 4 again, and for 0 1 has decreased. So this is the state I will go to, right? And this is valid. So this is a valid solution for this particular problem. But the thing is this the most optimal way in which you can solve? So of course there are multiple ways in which you can think about recursive problems, but is it the most optimal state? That's where like you need to think about what should I keep in state. So of course there might be multiple options in a different problem, but designing in the state is the most crux part of DP. Like what do you keep in state so that it works? And that comes with practice. It's not like you will just get that for every new problem. It comes with practice. But this is what is like one particular style that is possible. Another one is one that others suggested, that DP of I comma last character comma count of last character. So out of these two, both of these should pop up in your mind, and then you should be able to decide on okay, which one should I use. Okay, so if I think about this particular idea, the states can take n comma it's mostly uh, like k comma k. But the thing is, like if you save this, so the array will. So I'm not going into like this. If you write this recursively, the complexity would be similar to the other one, time complexity, but the memory would needed would be more if you save it in an array. But I'm not going into that right now. So this is more or less order n into k, right? Because these values can take this, and from every one of them you have 2 transitions, right? Now, of course, there is some constraints that holding true in this case, that either one of them will always be 4, and the other one will be like something less. So there is a lot of pruning that will happen, like across this all k square values, only like around 2k or 3k values can be taken, right? At most 3k or at most 2k values can be taken, right? So this is actually like n into k into 2 only, but if you try to save this kind of table with directly a 2D 3D table, it will give you a MLE. Okay, so like the memory limit would be something like m into k into k. You can save it into map, but that is something non-optimal directly. Okay, directly save. Okay, so in crude sense, let's for today assume that this is n into k square. Okay, so we will look into these kind of constraints in the next session, where we'll talk about optimizing DPs. Okay. Another state that most of the others suggested is something like, okay, similar to the last problem, that okay, I'm placing 0 0 1 0 1 1 1 so on, right? So if I think about this particular, like I have placed, let's say let's say 6 characters till now, so I'm building a recursion of this particular state. Okay, sorry, 7 characters. Okay, so with this 7 characters placed, I need to find out what is the next thing that I can do. So the only thing that is deciding to whether I can place a 0 or 1 at the end or not, okay, is the last character and what is its count, right? Like what is the last character and what is its count. So okay, yeah, this is actually like, if you just understand this constraint that one of them is always 4, then it is always n into k into 2 only. Okay, but the thing is, you have these parameters in the recursion, right? So you will have to create a 2D array, like a 3D array, to store it. So if you're storing it in an array, let's say today we are not talking about storing it into maps and other things, but if you're storing it into arrays, the states that you will visit is kind of like large. So it's like you have to create a n into k square into n into k into k array, right? So that is n into k square. So memory will exceed in that case. Okay. Is this clear, that what I'm talking about? Okay. Okay. So basically, when we are saying this is a DP, we will try to store the values, right? That what is for a I, what is for this K. No, this is not okay. I'm not talking about your particular state. That's working. This is a different state, right? Allowed ones and allowed zeros. This particular state is of course working. It's not. I think this we will continue. I think you have some confusion on that. I'm just clearing it off after this. So based on what is the last character? Last character. Uh, and what is this k, like last characters count. If you keep these two things in the recursion along with position, this is sufficient enough to decide on what you can place, like can I place a 0 or 1 in the last next one, right? And this will decide on which state I will go into, like whether the new last character will be 0 or 1, or what is the count of the new last character, right? So this is a more I would say like clearer state to take in this particular problem, because this allows us to, like, there will be only 2 values possible over here. There are k values and there are only like n values over here. So this is order n into k, because every time you have just 2 transitions, either append a 0 or append a 1, right? N into k. Okay, make sense? So this would be an order n into k solution, and you need to create a n into like something like this, n to k sized array to store the DP value. Okay, so this is more optimal because memory is also good, time is also good. In this case, memory would have, like, if you store it into 2D array, memory would have been larger. Okay, makes sense. So this is the way to keep things. So I hope by now you have got a sense that okay, the things in which you try to append things at the, like, this style of DP, that I'm trying to append characters at the end, and what is guiding the condition of putting a new character at the end, that what do I need to maintain, that okay, I need to maintain last character and its count so that I can decide on next one. So keep that things in the state. That's how you design into state, right? Like this is this making sense to everyone? How are we designing the states for these things? Can I have a quick +1 if this problem is clear? So n into k is the best we can do into this. Okay. So let's quickly move into the next problem. So let's say so this is a classical problem. So let's say there are like you have a keyboard, okay, and there are keys that you can use to like copy, paste, and everything. Okay. So now let's say you have a allowed number of keystrokes. Okay, there is n number of keystrokes that you can use. Like you can press n number of keys on the keyboard. Okay, the keys that are available is, let's say, uh, A. Okay, control A. So control A is there. Okay, control C. Okay, control V. Okay, so you can press these four type of combinations, okay, in one key press. Okay, either control A, control C, control V. I think you got the idea that what we are trying to do with these things. So basically this is similar to copy pasting. So we can use control A, control C, and then control V to paste things, right? Like this is a sequence that is going to paste, copy everything and paste things, right? Now uh, you can of course press a single character A to get something onto the screen as well, right? So let's say you have to make n number of key press and you have to print maximum number of A's on the screen. Okay, this is the target. Okay, just print maximum number of A's on the screen. So how do you, like, what is the maximum number of A's that you can print? That's the question. What's the optimal strategy, or like how would you go ahead and do the things? Because there is a lot of decisions that you have to make, right? Like either you can go about just pressing A's, or at some point you can stop and just use control A, C, and then control V. Like you can press control V once, you can press control V twice, and so on, right? You can press control V multiple number of times to get some sequence. So find out the number of times, like number of different ways in which you can pick up press, and out of all those you need to find out the number of maximum A's you can print on the screen. Okay. Is the question clear to everyone? That you have to make n keystrokes, these are the four keys, print the maximum number of A's onto the screen. That's all. Okay. So how would we solve this particular? Not necessarily, it's not always optimal. So basically, so let me give you an example like why it might not be optimal. Like I'm not giving you a big example, but I will give you a sense that why it might not be optimal. So there might be a sequence that, okay, you press some number of A's, then you press control A, control C, okay, and then press control V two times. Let's say you press control V twice. So these many sequences would be pasted twice, right? So it might turn out that, okay, like just the last one might not, like doing a control V at last just once might not be optimal. So how do we take into account these things? Any ideas? So this is also some sort of sequence that we are creating, right? A sequence of four, like there is like any possibility of, out of all different possible four character presses, like appending a B, 1 2 3 4, find out the one that prints the maximum number of a's, right? That's the target. Okay, so this is like kind of the space in which we are searching. Okay, there is like every character can be 1 2 3 4, find out n length sequence which prints the maximum number of a. So now let's talk about what can be our possible recurse, like optimal DP kind of state. Okay, what should we type of keep in DP state? So let's try to like think about the most standard state that you can think of. That what is the maximum number of maximum A's I can print with n moves? So this is also a valid state, right? Like we can just say that this is what we are creating. Okay, DP of n says the maximum number of A's I can print with n moves. Okay. And this is what is in fact the desired question. So in a lot of problem, when you're starting out, like just keeping the thing that is required in the state is okay. Start with that, and then you will see that okay, while designing the transitions I'm facing something problem, so I might need to keep things in the some more things in the state so that I can design the transitions and so on, right? So in a lot of problems, taking the thing that is given as the input in the state works most of the time. Now think about it. Like of course the total number of sequence, like there is some sequence and it can end with 1 2 3 4. Okay, there are only like for any n length sequence, like you will do n minus 1 moves and then it will end with either move number 1 2 3 4. Okay, now out of these four, which is definitely not optimal? Out of these four, which of the following, like which of the moves is definitely not optimal? 2 and 3, right? Like what is the point in doing control A or control C in the last move? I could have just pressed A instead of that and I could have created something better, right? Is this making sense to everyone? Can I have a quick plus one if this is making sense? That in the last move, what's the point in doing a control A or control C? It's not going to give me another A, right? It's it would have been rather better to just do a control V or maybe just press a single A. That would have given us a better A sequence, right? Okay. So it's never optimal to use like control A or control C in the last move. Is this clear to everyone? Can I pick plus one? Because this is a very nice observation that you need to understand. Once we are done with this, we can design the transitions fairly. So one more thing that you can think about is like let's say there is a sequence that is going on and then you have some sort of like uh now of course like if you are doing control A, you will do control C, right? Yeah, exactly, that we are coming to that. There is no point in doing like control A and then control C and then leaving it, or maybe just doing control A. What's the point in doing control A if you're not doing control C, right? So first of all, control A control C will definitely come together, right? That is definitely optimal. Okay, that like there is no other thing that you can do. Okay, after this you might press just A or control V, like 4. Okay, either you can press 1 or 4. Okay, so if you have taken at least one character into your buffer, like when you are like doing control A control C, then of course doing 4 is always better than doing 1, right? If you have taken at least one character into hold, doing the 4 is always better than just pressing 1. Is this clear to everyone? So once we do control like 2 3, instead of pressing 1, it's always better to press 4. Okay, like for like after doing this last like I'm not talking about all of these things, keep this in mind, I'm not talking about this thing. I'm currently saying that okay, the last time I did control A control C, after that let's say I'm not doing any control A control C. Okay, so after that I would always do control like just 4 only. It's always better. Is this making sense? Is this clear to everyone? Can I quick plus one if this is clear? That after like after control A control C, in the last time that I did a control A control C, I would be using the move 4 only. Now if this is clear, we are done with the problem. So think about this now, that dp of n gives you the best you can do with n moves. Okay, so of course the one way would be the last move is a single one. Okay, you just pressed A, so this would be nothing but dp of n minus 1 plus 1 length, because you pressed 1A, right? This is one transition that is of course like this is always valid. Okay, or else we will try to do like control A, control C. Okay, and then a bunch of v's. Okay, a bunch of control v's. Okay, let's say x number of them. Okay, so like this is at the end, like at the end we are doing, like we are doing 4. Okay, so let's say we were doing some x number of 4s, and before that we did a control c, like control A control C to load things into the buffer, right? Okay, now let's say if you're doing x number of things, x number of times, what is the total number of moves that we are taking? X plus 2, right? X plus 2 number of moves. So what is this like buffer, like this loading into buffer is going to take into its buffer? That is nothing but dp of n minus x plus 2. Because if we are doing x plus 2 moves, if we are doing x moves of v, we are doing x plus 2 number of moves of in total at the end. So before that, whatever we did out of this n moves, that is going to get into like whatever best we did in this n minus x plus 2 moves, that is going to get loaded into the buffer. And then every time you press this v, that is what is going to get pasted, right? So this particular number, let's say y, is going to get pasted. There was initially this already pasted, and then you pasted it x more times, so it is going to get pasted x plus 1 number of times, right? Okay, so if I write this in like just dp sense, just quick recurrence. Okay, I am having n. I can either do like a dp of n minus 1 comma plus 1, or I will do control A control C and just one v. Okay, so in that case I would do dp of n minus 3, then I did a control A control C, and then I did a control v. So whatever I had at n minus 3, it got doubled, because control b plus v will give me a double, right? Or I can go to dp of n minus 4 and do like last two moves would be control v, so that would give me this multiplied by 3, right? Basically I'm basically looping over all different possible dp of n minus I multiplied by I minus 1. Okay, whichever I is valid. So I can go only up to n, right? Like dp of 0 is of course 0. Like in 0 move you can print 0 A's and just loop over all valid things. Okay, so this is all things that I can do at this position, and I will take the max of all possible things. That's it. Okay, so this is how you should be thinking about like problems where you have to do moves or things. That okay, what are the moves that I will do, and like I already have the smaller instance optimal answer, right? That in this many moves, how can I do the best thing? So after that, I will do control C, control V. Okay, and this type of thinking, that you should keep in mind, that instead of doing a lot of different random things, I should always do things that are like optimal. Like it is of course optimal to like press 1 or 4 out of 3, 2 and 3, right? So it's, we are never going to do that. So pruning of these obvious things sometimes helps you to think about these cases, that okay, it can only be like a lot of A presses, or I will do some control C, control V, control A, control C, CTRL, control A, control V, and then I will do a lot of control V, control V, control V, and all, right? So first we ruled off this, and then we say that okay, after the last control A, control C, I will do only control V. So just based on that, I'm writing just the recurrent states, right? That's it. That's the total number of transitions. Is this clear? So is this clear to everyone? Can I have a plus one if this is clear to everyone? If you have any doubt, you can quickly ask that. this is more or less what I thought of discussing. I have few more problems. We can discuss few more, but I think we have discussed a lot of things. So I would rather take up some time to revise on different ideas that we talked about today. We will of course take up more problems on the next session. Okay. So let me quickly go back and we talk about things that we discussed. Okay, so that it all gets with it all stays with you a lot of for a long time. Okay. So of course these are the things. So if you think about it, we almost discussed all the problems today in the lines of keeping like a dp of I. Okay, so whenever you are having a problem, like just think about keeping dp of I first. Like it's the most natural state that comes up in mind. Okay, once you have dp of I in the state, you need to decide on what, if you need to keep something else or not. How do you decide on this? First try to design with just dp of I, try to write a brute force kind of code and see that okay, what are the things in the like complete solution that you're keeping that you need to check so that I can get to the solution. So that check sometimes reveals that okay, what do I need to keep track of. Okay, so in knapsack, can I take the ith item or not, depends on how much weight I have taken and what is the allowed total weight, right? Based on that I can take this item or not. So I need to keep total number of sum of weights, right? Also, like what is the best you can do at ending at I is also one possible configuration at I. So that was the case in the first problem, that what is the minimum number of moves that you can do from that, in which you can move to reach to some index I. Okay, we just have 3 transitions possible. Okay, also you can design from I what is the best I can do, that we have some sort of like 3 transitions in this case as well. Okay, then we talked about like in this kind of like configuration setups where you have to like find out the number of different possibilities. So try to decide a recursion kind of setup where like I will keep I in the recursion that I'm trying to put up things. With that I into recursion, I'll just try to place as many things as I can, and at the end I generally check whether my solution is correct or not, right? That's what we do in recursion, that try to place things. If you remember even the most standard NQueen problem, try to place things and at the end check whether it's valid or not. That's what we are even doing in this, right? So in the balance parenthesis sequence, just place things at each position and then check. So just to optimize on check, we talked about that in parenthesis sequence. We can talk about like these opening and closing techniques. This is a very important technique and this will help you in a lot of different problems, irrespective of its DP or not in balance parenthesis questions. Okay, that +1 -1 relevance. Okay, converting into +1 -1. So I generally think every problem of balance parenthesis in this sense. Okay, okay. Now with this in check, you have some sort of yeah. So you have the count of the open brackets. That is what is going to be relevant, right, with this setup, because we know that how we are checking a balance parenthesis sequence. I'm coming to that. Okay. So checking balance parenthesis sequence comes down to finding out the opening like it only depends on the number of unclosed open brackets. It should not never go to less than 0. That's it. Okay, and if it's 0 at the end, then we are getting a correct solution. So it's the only thing that I need extra apart from the position to check whether my solution is correct or not, right? So that's how I'm designing the state for this particular problem. This is just the implementation. Okay, so this is the total state. Okay, coming to the next problem. Okay, so I'm not saying I'm just doing control A, control C. We will come to that particular problem at the end. Okay, so just stay for a few more seconds. We'll come to that. Okay, so then we talked about this distinct subsequence problems where number of different subsequence of a string, how many are there. So that particular problem, we just talked about some iterative style, that if we have some set and we are incrementally expanding it with every character that is going to get appended, right? So this is an idea that comes up quite often in case of even simulation problems as well, that okay, I have something till now, if I add a new element, what is the new configuration that is going to come up? So this is the new things that are going to get added up, right? So we look at new things that are going to get added and we come to a conclusion that of course it's trying to double everything because we are going to append it at the end. Only thing is, the last time it occurred, whatever that introduced, like what are the new elements that it introduced, those are the things that is going to get introduced again. So we just subtract that. Okay. So that's what is happening. In fact, this tried to introduce dp of I minus 1, those things. So these all characters got already expanded. So you just need to subtract that. And that leads to a very simple dp. Okay, once you get this observation. Now we talked about few problems of placing zeros and ones or twos into sequences. So in that particular case, we looked at that just knowing the last character helps. That okay, if you know the last character states like just a 0 1, which character it was, based on that I can decide on whether I can place what is the choice I have for the next characters, right? Now this particular problem that you have to place, this is nothing but the placing zeros and ones only. Okay. So after placing one, you have just you cannot place another one. That's how you can decide. Okay. Now no k consecutive, so you need the count of last k numbers into place. Okay. If you know the count of last character, then you're done. Okay. And then we talked about this control A control C problem. This is this is a standard problem. In fact, like this comes up in a lot of interviews. Not a lot of, but this is a very standard pick for a interview question. Okay. But still, the idea is that when you're seeing such problems, you first need to like rule off the obvious ones like these. Now after doing control A control C, so let's talk about this particular sequence. That there is a sequence, then you do this is the last time you are doing control A control C. Okay, there would be some last occurrence of control A control C, right? So after that you can do either control V or you can press A. Okay. Now after doing this last occurrence of control A control C, can I say that pressing A and then control C, like control V is same as, sorry, this particular part? Yeah, control C. I can do control V and then control A control A. Sorry, not control A, just A, right? These two are going to print me the same number of A's. Is this clear? First of all, is this clear, Benny? Because
So it is
yeah,
the last time we are doing control A control C, right? Because
yeah.
no, my doubt was once we keep doing control C, the number of A's is linearly increasing. It will become 2 times, 3 times, 4 times.
Yeah.
But if after doing control A control C control V 3 times, it's going to double each time, right? The increase will be exponential. It will be, we'll have 2 times the length of A, then it will be 4 times length of A, then 8 times length of A. Then after that, it is more profitable to do control A control C control V again, right?
Yeah.
But what you meant was the last time AC is occurring the last.
Yeah. So we are breaking it on the last time A and C is occurring. After that we are doing, so this all that we talked about is the last A and C, right? That after that we are doing VVV and we are closing it off. So for the last x plus 2, this is for the configuration, and then before that is going to given us by this DP. So that DP can use another control A control C in a nested form in itself, if you think about it, right?
So x should not be greater than 3, right? Because if that's possible, then we can do another control A control C control V. That should be better than not 3. Sorry,
yeah.
it should be
yeah. So basically, that is some more pruning that you are doing over there. But of course you have to take care of these cases. Like there might be some more cases that is coming up. So this kind of recursion covers them all, right? Yeah. That what you're suggesting is, of course, it's better to do like after some time, if you have a scope, do a control A control C, and then it's better to it will grow even faster, right? That's what you're saying. Yeah. So that's of course true. But again, in a lot of so that might help, like you might go into thinking that okay, some sort of greedy strategy might be there. But again, when you have some DP strategy that enumerates on all possible choices, you should always go forward with DP strategy. Okay. Like in some question, if you have a constraint which allows you to use, you are thinking of some greedy which is passing, and you also know some DP which is passing, always go with DP, because DPs are enumerative and it covers all of the cases. So that's why you will never it's a lower chance of getting a WA or something like that, right?
Oh, okay. Yeah, since this is DP, even that bottom size thing will also be covered in this.
Yeah, exactly. Yeah. It covers everything. So DPs are mostly like a pruned enumeration, right? That you are doing enumeration on every possible solution space, just a pruned one. So always prefer DP over things like that. You might not be able to get like after how many things, like if you have like five, then what should 5 or 6? What should I do exactly? It's confusing. So it's better to write just a state. Okay. Of course, just a quick last question: what would be the complexity of this particular DP? Anyone? Any ideas? So there are like these many recurrence, and you have state. So we just use the formula, right? That number of states multiplied by average number of transitions. So the number of transitions is linear. Like it goes up to like until this becomes dp of 1 multiplied by n minus 3. So n into n. Yeah, it's so average number of transition is order n, number of states is order n. So this is going to be an n square, right? This is going to be an n square d. So I think that's all for today's session.